Welcome ENET 130 at Bellingham Technical College. This is another recorded lecture in our study of semiconductors. This is drawing from our textbook by James Fiore on semiconductor devices, and it's chapter 5 on biasing bipolar junction transistors. So the whole reason we're going to discuss biasing is in the context of amplification, which is one of the main uses for any transistor, and definitely the bipolar junctions. So we've got to ask ourselves, why bias? What's the point? Why do we need to apply all these DC voltages and have resistors in line with our collector and emitter and base? What does that do for us in the context of we're going to put a signal, an alternating periodic AC signal into our base at some point, and want to get an amplified result somewhere out of the circuit later? Well, in order to understand biasing in the context of amplifying a signal, we need to think about what it takes for a signal. Go back to our basic transistor function. What does it take for a signal at the base to open the transistor? So we can remember that our BJT will only open and allow current to flow from collector to emitter, or emitter to collector, depending on the PN, if we're applying a forward bias voltage at the base emitter junction that is sufficient to overcome the forward bias of that PN junction. Well, most silicon devices, that's 0.7 volts. That's almost 0.7 of a volt. Most very small signals that we'll be working with that require amplification aren't ever going to touch that. So we can apply our signal to the base in hopes of getting an amplified signal collector to emitter, and we'll get nothing because the transistor won't ever open. So that's kind of shown here a little bit in this figure, where we have an AC signal with a zero average voltage, and we'll blow this up a little bit so we can see it. So here's our signal needing amplification, and it's symmetric around 0. And this dotted line is our 0.7 volts to open the transistor, to get current flowing from the base to the emitter. There's our forward bias, probably 0.7. So the transistor is only going to open when that base emitter junction is above that dotted line. If we're relying on our signal to provide that, we're going to cut off the whole bottom half. We'll only see those very top portions. We won't get the entire negative half cycle. It will be gone. So if we wanted to amplify this entire signal, we would need to shift the whole signal up so that the whole signal is well above our forward bias voltage at our base emitter junction. So we can't rely on our signal itself to open the transistor. We're going to have to apply some DC bias voltage to open the transistor. Then we can put our signal through, periodically oscillating around our bias voltage, and we can amplify the whole signal because it's all above the forward bias voltage. So we can think of biasing as lifting our AC signal with an effective DC offset, so it's all above our V forward bias. Okay, so in practical terms, how do we do this? How do we achieve this nice V bias at our base so we can superimpose our AC signal on it at some point? How do we get that to work in a practical circuit? Well, obviously we could just put a DC source right at the base. And how would do it? Add the AC to the DC, very similar to what we saw with offsets on our clippers and clampers. Challenges to that: keeping that bias voltage stable under different circuit operating conditions. And the biggest challenge to that is the fact that our beta will change. So if we are simply applying one bias voltage and then we operate the circuit, this could easily change as a result of changes in beta. If you remember our Q point, that's the voltage drop collector to emitter versus collector current at the operating point, that's dependent on beta. Our saturation and cutoff is dependent on our external circuit. So if beta changes, our operating point will change, and it's very likely that this will change and then possibly have our signal not all be where it needs to be. So we're looking now not just to lift our future AC signal so it all gets amplified, but we also want to add portions of our external circuit that will give us a stable collector current even if beta changes. So as remember, beta of any transistor device is itself dependent on I sub C, our collector current, and on temperature. Both could change in operation. We don't want our beta to change just because we move the Q point. We want to operate in a different regime. So the rest of this lecture, and in fact the rest of Fiore's chapter 5, goes through different practical ways to achieve this in the context of different examples of circuits. So we're going to march right through those, and I'll walk you through the basics, and then one example, and then maybe leave a second example for you to work through. And then of course there's lots of practice problems. So most of these methods involve utilizing Kirchhoff's voltage law over and over again. That is essential. At this point, everything is DC, so we don't have to worry about phase angles, and we don't have to worry about differences in behavior of reactive components with frequency. But we do need to think in terms of what we do and don't know about different points in the circuit with their voltage and current, and especially voltage relative to ground. So things to remember. The voltage drop between our collector and emitter in our transistor is a function of the circuit operation. We never know that. We have to always get it by difference. We always know, on the other hand, we always know the voltage drop between the base and the emitter, because that is merely the p-n junction forward voltage for our type of device. So 0.7 for silicon, 0.3 for germanium. So we are always going to build our Kirchhoff's voltage law loops around the base emitter junction when we try to solve for our different supply voltages in terms of current. So we're not doing this just to analyze the circuit, by the way. We're going to do some circuit analysis, definitely. But what we're going to try to do is work out relationships between these supply voltages and these resistors, because these are selectable. We can choose whichever ones we want when we build a circuit. What we want to do is understand how these values, these are our biasing supply voltages and biasing resistors. How do those affect the relationship between a base current, a collector current, which is generally the thing that's going to get amplified, and the collector emitter voltage drop? Because those will be the things that will determine what our circuit output is in terms of an amplified signal later on, which we'll get to in the next chapter. So we're going to work out a lot of relationships between VCC, collector supply voltage, VEE, emitter supply voltage, and our collector and emitter and base resistors. So we understand something about our output signal versus all of those. Okay, so with that great intro, we're going to start out with this one. This is called a two-supply voltage source emitter bias. So we've got a supply voltage added to the collector and a supply voltage to the emitter. Very important. The emitter is basically, its supply voltage is in what we could say backwards. So we are supplying a voltage that is below ground at this point right here, at this red point. Ground is 0 by definition, and we basically have the negative terminal facing away from it. So we lowered the voltage at this red point. The collector, we raised it. Current is going to flow in the direction of the arrow of the transistor, so we're going to end up with a loop that flows like this. And of course we have our loop number 1. So the orientation of these sources is very important. But of course we're not going to start with that loop. We're going to start with loop number 1 because we have the all-important base emitter junction voltage, which we know. If we started with this other loop, we'd be dead in the water because we don't know the voltage difference between C and E. So let's start with KVL loop number 1. So we're going to start at ground, and we're going to drop a voltage over resistor B. We're going to drop voltage between the base and the emitter, voltage drop, and we're going to drop voltage over RE, and we're going to add voltage going through VEE. It's going to raise us back to ground. Okay, so we'll write VEE in terms of the other voltage drops. So the voltage drop over the base resistor is the base current times the base resistor, Ohm's law. The base emitter junction voltage is going to be a function of our device, probably 0.7, and our voltage drop over the emitter resistor is going to be that resistance times the emitter current, Ohm's law again. Great. So we can drop those in and have one big expression. So our emitter source voltage is going to be equal to the base current times base resistor plus emitter current times the emitter resistor plus base emitter junction. And for a large beta, we know that collector and emitter current are approximately equal. So we can put I sub C in for I sub E. And we have an expression that includes just I sub base current and collector current. Then we can use our definition of beta and substitute in for base current. And now we have an expression for collector current, which is something we always want to know about our amplifier circuit in terms of our emitter supply voltage, our beta, our base resistor, and our emitter resistor, and our base emitter junction. So we can rearrange terms to write I sub C in terms of all of these other things, and we get this expression. So for that configuration of circuit, here's our collector current as a function of one supply, base emitter junction, and two resistors. Notice that our collector current was not at all dependent on that collector supply voltage. Interesting, huh? And this holds, by the way, for PMP, except the voltage polarities that the supplies would change. Okay. So is this collector current going to be stable if beta changes? That was one of the things we wanted to achieve. Well, beta is usually a pretty big number. So if the base resistor is anywhere close to the emitter resistor, then this will be true. So if beta is like 100 and the base resistor is 100 ohms and the emitter resistor is 100 ohms, this is going to be 1 plus 100. Not very much. So generally speaking, if the base resistor and emitter resistor are similar magnitude, not like an order, if the base resistor isn't like 2 orders of magnitude more than the emitter, then this term kind of goes away. And we end up with a beta-free expression. So we can choose our base and our emitter resistors to give us a beta-independent collector current. Now we're stable. If the transistor heats up a little, beta changes, collector current is not going to change significantly. So we've now achieved stability. So that was one of our goals. Okay. So what else can we say now that we've gone through our KVL loop? We might want to say some other things about this circuit. So we've reproduced the circuit over here, very simplified, and sorry for the condensed picture, but we have ground, here's our collector supply, collector resistor, and then point C, which is our voltage at the collector input to the transistor. Point B is our base voltage, and these are all referenced to ground, B, C, and E, and our supply base. So here's a simplified schematic. So here was our, from the other page, our simplified, if R sub B and R sub B are similar, our beta independent collector expression. We can use this to plug back in and get emitter current, base current, and the voltages at these 3 points, as well as our collector emitter voltage drop, all of which are important. These 3 in particular we'll build on when we start amplifying, because these will be the basis of voltage gain for a given signal input. So we'll need to know what these are later on when we actually turn these circuits into amplifiers. So knowing that we can evaluate them is really handy. So let's start out with an expression for V sub C, and that's easy because we will use Kirchhoff's voltage law again and start with ground, and then we'll rise through our collector supply, and then we'll drop over our collector resistor to get to point C. So it's just simply collector supply minus collector current times collector resistance. And we can do the same thing with the emitter. Ground minus the emitter, because remember it's in backwards, plus, because we're going swimming upstream against current, plus emitter current times emitter resistance to get to point E here. So we're just applying Ohm's law to the circuit, and we can have an analogous expression for V sub B going from the base, because we know what the voltage drop base emitter. So it can go from ground at 0. We can drop our base current times our base resistor. We can drop the base emitter voltage and arrive at point E by a different route. So because V sub B emitter voltage is emitter voltage versus ground, however you calculate it, we can now relate our emitter current to our base current, and because our emitter and base and collector currents are pretty much equal, approximately equal, we can relate collector current to base with another expression. So we can get our collector emitter voltage drop just by subtracting our collector voltage from our emitter voltage by difference. Voltage difference, that's what VCE is. It is a voltage difference. So I just take this expression and I subtract that expression. And I have a nice expression relating collector emitter voltage drop to my supply voltages, my biasing resistors, and my current. So that gives me a defined Q point. And load lines are DC load lines, so that's our maximum current that the circuit can give independent of beta, and the cutoff voltage, the collector emitter voltage that we would need to stop the collector current, again independent of beta. We can also get those just from a KVL loop, again starting at the collector supply. We can say if we want to go for saturation current, we assume no voltage difference across the transistor. VCE is 0, so we would just say the collector supply voltage minus collector current times R sub C minus 0, because VCE is 0, minus I sub C times RE should equal our emitter supply. So we just do a straight KVL between the two supplies. And of course, if we want to shut off the collector current, we know we would have to apply a voltage here between our collector and emitter that is equal to the sum of our two supplies, because we'd have to be bucking them both. So, and you can just literally write that coming out of Kirchhoff's voltage law the way we did in the previous chapter. So we end up with these two expressions for cutoff and saturation for that particular configuration. And depending on our beta, we'll be operating with a Q point somewhere in here. Okay, so here's a numerical example and a little bit different circuit drawing, pretty much the same. We've got a 20 volt collector supply, transistor beta of 100. We've got a 3.3 kilo ohm collector resistor, bias resistor, 5.1 kilo ohm base resistor, 2.7 kilo ohm emitter resistor. So first thing to check, was the base resistor and the emitter resistor pretty similar? Yep, that'll be helpful when we want to make ourselves beta independent. And then 10 volts emitter supply oriented backwards to ground. So plot a Q point and get the load line, meaning ISAT and VCE cutoff. So as usual, we're going to start with KVL loop number 1, where we know that base emitter voltage drop. So we're going to start at ground, 0. We're going to drop a voltage equal to base current times the base resistor. We're going to drop the base emitter junction, which we're going to assume is 0.7 volts, because we're going to assume we have a silicon device if we don't know otherwise. So we're going to drop there, and then we're going to drop voltage equal to the emitter current times the emitter resistor. Then we're going to rise 10 volts going through the emitter supply. So our starting expression. We're going to make our assumption that emitter and collector currents are pretty much the same, and we're going to assume that we can write collector and base currents in terms of each other with beta. So that'll give us one equation and one unknown. We can write it in terms of beta, or excuse me, I base current, base current, and then we can get collector and emitter currents by just multiplying by, in this case, 100. So we can go back into our KVL loop. If we know the base current, we start at ground and we drop base current times the resistor, and now we have the voltage at the base. So that's negative 0.17 volts versus ground, where ground is 0. We can do the same thing for the collector. We're going to start at ground and we're going to rise 20 volts, and then we're going to drop our collector current times 3.3K to get to this point, which is our collector voltage point. So that's what we did there. So our collector voltage is 8.8, about 8.85 volts, give or take. And last but not least, the emitter. We can start at 0, we go down 10 volts, and then we go up the emitter current, which is the same as the collector, times 2.7 kilo ohms to get to our emitter point. And that ends up giving us negative 0.8724 versus ground. So collector to emitter, we say V sub C minus V sub E, which actually gives us something more than V sub C. So here's our collector emitter voltage drop. Here's our I sub C. So this is our Q point. So if we want to know our load line limits, all we have to do is assume for our saturation current, assume that the voltage drop between our collector point and our emitter point is 0, and then solve for the current flow along this path. So 20 volts minus saturation current times 3.3K minus saturation current times 2.7K plus 10 volts equals 0, which is what we did here, and solve for IC sat, and so we get about 5 milliamps, and our Q point was operating at about 3.3 milliamps, so not that different. And then we can get a VCE cutoff. In this case, it's equal to the combo of the two supply voltages, so that's 10 and 20, that's 30. So if we wanted to plot this, there's our cutoff, here's our saturation. So again, cutoff and saturation are totally independent of the transistor. They're dependent on the external circuit. They're the max current and the collector emitter voltage necessary to stop current, and depending on our beta, we'll be operating somewhere in between. So the Q point that we calculated for our particular circuit is, kind of up at the high current end. So lower voltage, higher current. Okay. So there is another example that I will let you walk through that's very similar, same kind of approach to supplies, and you can get your Q point and load line. Okay, as nice as it is to have two tunable supplies, power supplies are kind of expensive, and especially if we need to miniaturize them. So if you have an electronic device, you might want one supply for the whole device, and you may power several transistors off of it. So there's a real advantage to only having one DC biasing supply. If we want to take that supply and basically use it at multiple points in our circuit, we need to use voltage dividers. So this is a biasing method number 2, the voltage divider. So you can see we have again a transistor with our biasing resistors, but this time we only have one supply. So we've put it on the collector, so this is the collector DC supply. So it's positive versus ground. And the base voltage is going to be dependent on the ratio of R1 and R2 and our collector voltage. So basically it's one supply doing the work of two. So we can start the easy way looking at our cutoff and saturation conditions, because those don't care about the divider. For saturation conditions, we would assume that the voltage drop between C and E is 0, which means saturation current will just be our collector supply minus saturation current times R sub C minus saturation current times R sub E, and then we're at ground. So for that, we can write an expression. Saturation current is just our collector supply divided by the two biasing resistors, collector and emitter. Cutoff voltage is even easier. It just has to be the collector supply. If the VCE is pushing back the same as VCC, no current flows. So we know what our load line is doing. So now we need to wrangle with our voltage divider a little bit to be able to analyze the circuit at particular operating points that will involve our Q points that will involve using the transistor beta. Okay, the easiest way to do this is to Thevenize. So we're going to Thevenize this portion of the circuit, including the collector supply. We're going to Thevenize around point B. Remember, a Thevenin equivalent is an equivalent series voltage source and resistor in series that are taken from the point of view of the component or the point in the circuit around which you are Thevenizing. So it all depends on the point of view. In this case, it's the point of view of B, which is the base voltage, just so happens to be, because that's what we want it to be in the circuit. So here is a little reorg of what's in this dotted line, the dotted group over here, just written from the point of view of B. And so I'm going to put a dashed line around it so you know it's the same thing. Same part of the circuit, just written a little bit differently, so it's easier to see how we would Thevenize it. So remember, for a Thevenin equivalent, we want to get this over here. So step 1, we would think, what is the voltage at point B, assuming everything else in the circuit is what it is? Well, that's pretty easy. It's a voltage divider. So we would say the voltage at point B is a current flowing through R2 above ground. Current flowing through R2 is VCC divided by R1 plus R2. So VCC divided by the sum of R1 and R2 times R2 gives me my Thevenin voltage. My Thevenin resistance, I would short the voltage supply and look at the equivalent resistance from B back to ground. That puts R1 and R2 in parallel. So just parallel resistor formula. With DC, very easy. No phase angles necessary. So that gives me a formula for my Thevenin voltage and resistor equivalent. Now, rather than having this divider, I have an equivalent source and single resistor that I can plug into my circuit and make it look like this. now I have something that I'm used to analyzing. I can very easily calculate V sub B by just saying it's V Thevenin minus the current flowing over the R Thevenin. And of course I already know what those are in terms of my VCC and my two voltage divider resistors. So now I'm just going to apply the same principles. I'm going to KVL loop number 1 the same way I did in my two supply example, my two supply bias. So I'll start by rising up through my V Thevenin and then dropping my base current times R Thevenin. Then I'm going to drop my base emitter voltage junction, my forward bias, which I'll assume being silicon device 0.7. I'm going to drop by my emitter current times my emitter resistor and down to ground. Assume collector and emitter current are similar, and furthermore that collector current is beta times base current, basic BJT principles. Now I can plug those back in and I should have only one unknown, which is I sub C or I sub B. I can solve for either one, and I can get an expression for I sub C in terms of my Thevenin equivalent voltage and resistance. So now if I wanted to determine whether or not that collector current was beta independent, I would compare the values for R Thevenin to R sub E, and if they were similar, in other words if R Thevenin wasn't like 2 or 3 orders of magnitude bigger, I could say I was beta independent and say that R sub E is much bigger than this. Probably is, because beta is going to be at least 100. So we can step through this with some numbers. In this case we'll start with a 15 volt supply. R1 and 2 are about 10 and 4.7 K apiece, and then comparable values for collector and emitter bias resistors. So we can go through the same exercise, Thevenizing around our supply and our two resistors. We can plug that back in and get an I sub C and an I sub B. We don't need our Thevenin to get our saturation voltage and cutoff, and we can go back to our KVL number 2 once we have our I sub C and calculate our collector emitter voltage drop at our Q point, at our operating point, and get 6.1 volts. So we're right in the middle of the load line. So obviously the trick here is getting our Thevenin equivalent. After that it's a pretty trivial exercise in just a couple of KVL loops. Okay, looking at another example, and this is example 5.4 from our chapter 5 in our theory book. It's another example of voltage divider biasing. Looking at forming the Thevenin equivalent. Okay, apologies for the pause. This is basically the same circuit, example 5.4, but there's more detail given about how I got the Thevenin equivalent. So our R Thevenin of 3200 and V Thevenin of 10.2 that ends up going into our simplified circuit. So otherwise very similar procedure to up here in 5.3. We had a different Thevenin equivalent. So made for different answers coming out of our circuit, but otherwise once we got our Thevenin equivalent the analysis was very, very similar. And for those of you who don't like Thevenin equivalents, this is basically your alternative. Between these two bars is what's actually a nodal analysis that you could work through that ended up being 4 equations and 4 unknowns with lots of math that was really only practically to solve with a simplifying example that there was very little base current relative to the total current flowing into the divider out of the collector supply. If you assume then you basically got the same V Thevenin that we got from our simple Thevenin analysis. So Thevenizing is definitely the way to go in these types of simplified or circuit analyses. And of course that assumption was what's called the lightly loaded voltage divider, meaning that the load on the divider, which would be the current flowing from our divider point into the base, was very small, which is reasonable. Base currents tend to be small. So if you want to step through this example on your own, 5.4, you can get your own Thevenin equivalent, go through the steps, and then find your Q point. Okay. Last main method of biasing, this is called feedback biasing. This is very important because not only do we get some circuit stability in the fact that our beta is relationship to our collector current is going to involve beta being down in the denominator of a fraction, kind of a double fraction, and being inconsequential if we choose the right value for base resistor versus emitter or collector. We're also going to get another measure of stability in that we're going to set up a condition in which our base current, which basically is our driver for the circuit, is going to be inversely related to the collector current. So the more collector current we have flowing, the less base current, so the less demand from our collector current, basically speaking. So let's take a look at how this works. This is a simple mode. This is called collector feedback. So we have our collector supply, our collector biasing resistor. Our base biasing resistor is going to attach the base to the collector. So this is the lead going into the transistor collector. We don't need anything else in this circuit. So we can define 2 KVL loops, one going from the collector to ground, and the other going from the collector through the base resistor and then through that base emitter junction, of which we know the voltage, and down to ground. So let's start with KVL loop number 1 that we won't be able to solve for except in a condition where VC is 0, but we can write it out. So we start with our collector supply. We drop, depending on the collector current flowing through R sub C to point C, and then if we subtract our voltage drop collector to emitter across the whole transistor, we get to ground. If we define the voltage at C is effectively, in this case, is equal to the collector emitter voltage drop, because there is nothing else in the circuit between it and ground, we can substitute V sub C in for VCE and say the voltage at point C is just simply the collector supply minus collector current times collector biasing resistor. So if collector current goes up, the voltage at point C goes down. They're inversely related. So let's go over to KVL loop number 2, where we're going to look at voltage drops along this path. So we can define voltage in terms of V sub C just starting here, because we're going to want to compare that to what we had over there, but we could have started at VCC as well. But if we started instead of up there, let me erase this. This time I'm just going to start here. So if I start at the voltage at point C, which is a collector voltage, and I'm going to drop base current times the base resistor, voltage drop over that resistor by Ohm's law, and then come around the circuit, I'm going to drop voltage equal to the base emitter junction, the forward biasing, and to ground. Kind of have a couple of arrows, we just need one. So we can write Kirchhoff's voltage law expression that includes that, V sub C minus base current times base resistor minus base emitter junction voltage. So I have two expressions for the voltage at point C, otherwise known as the collector voltage. Well, V sub C is equal to V sub C. So I could set these two expressions equal, and I could get some information about base current, collector current, in terms of each other and in terms of the supply voltage and resistors. I can also say something interesting about what happens to base current just by looking at these expressions. From this expression over here, I notice that if collector current increases, collector voltage, V sub C, goes down. Okay, if V sub C goes down, coming over here, then that means base current has to go down. Base resistor isn't going to change, that's a solid resistor. The base emitter junction voltage is not going to change, it's a characteristic of the transistor. So by the associative law, I can say if collector current goes up, then collector voltage goes down, and because of that, base current goes down. Remember, collector current is related to base current by beta. So I now have what's effectively a negative feedback loop. So if my collector current goes up because of something in the circuit, something is hot, whatever, I now have a base resistor that is positioned such that it is going to signal for a lower collector current. So that gives me an additional means of stabilizing the circuit. So I can continue with my cool equations that I already have written and just go ahead and write that relationship out, setting the two expressions for V sub C equal to one another. One from our KVL loop number 1 and KVL loop number 2. I can put in my relationship between base and collector current in for base current, and now I have an expression for my collector current in terms of all kinds of other things that are set in the circuit. So I can simplify and isolate my collector current expression on one side, and I have another one of these very similar looking expressions where I have supply in the numerator, and then I have two resistors being compared in the denominator, and again here is beta in the denominator of a fraction that's in a sum. So unless my base resistor is very, very large compared to my collector resistor, beta is not going to matter because it's large, and this expression will effectively might as well be 0 compared to this expression. So we are independent of beta. So we're going to be very stable for two reasons. Our saturation current is pretty easy to calculate. I assume that there is no voltage drop between point C and ground. VCE is 0, so my saturation current is just my collector supply divided by R sub C, my collector bias resistor. And of course, in order to stop the collector current flow, I would have to have a voltage drop collector to emitter equal to VCC. So, very simple expression for our load line limits. So we can go through some numbers here. So let's start with checking on, we've got a fairly large base resistor, so that is going to challenge our beta independence a little bit. But otherwise, we're about an order of magnitude difference between our collector bias resistor and our base. So we'll work through the numbers. We will go ahead and start with our KVL loop number 1, collector to ground, collector to emitter basically. So 15 volts at our supply minus collector current times our 10K collector bias resistor minus the voltage drop collector to emitter over the transistor brings us to ground. So we can substitute in an expression here based on what we know of basically the other way of getting from the collector to emitter, which is from this point flowing a base current through our base resistor and then coming over the base emitter junction, which is this. So all of that is the CE, because that's another way of getting from the collector to the emitter, and in this case, of course, the emitter is at ground. So VCE is the same as V sub C. So that's basically the drop through this path, which we know. We know all of the values. Base emitter junction, we can write an expression for the base current in terms of the collector current using our beta, and we know our base resistor value. So we end up getting this expression with just I sub C. So we can isolate I sub C, and so we're going to end up with 10K compared to 180K divided by 100. So that's going to be more comparable. End up with a collector current of 1.2 milliamps and a collector emitter voltage drop of 2.88 volts. So we can compare that to IC sat, which would be 15 volts divided by 10 kiloohms, which is 1.5 milliamps. So we're operating fairly close to saturation. We're at the upper end of the load line, and our cutoff voltage is 15. So we're a very, very small collector emitter voltage drop over the transistor. If we change beta from 100 to 50 and recalculated this, so we swapped this 100 out for a 50, we recalculated collector current, we'd get about 1.05 milliamps versus 1.2, only 13% difference. So, and that is for a fairly sizable base resistor. So we have a fair independence from beta for this circuit. So again, that's one of the goals of our biasing, was to make ourselves independent of beta. So we've certainly done that here. So last but not least, we have one other way of achieving feedback with our biasing resistors, and that's what's known as emitter feedback bias. And this is a schematic of how that's done. So in this case, believe it or not, the feedback resistor is this one. And that's why it's called emitter feedback. It look like it's in a feedback loop, but functionally it is. The way you can tell this from the one we just did, the collector feedback, even though we have our base resistor hooked up earlier in the circuit, it's hooked up directly to the collector supply. It's not hooked into V sub C. So that's the main difference in terms of looking at where we have our base resistor loop sitting. So this is a different configuration. It's going to give us a different dependence. So again, it's not intuitive just to stare at this to see how it's going to work necessarily. If you can, kudos. But a safe way to get the relationships is just, again, to walk ourselves through our Kirchhoff's voltage law loops. So we're going to start with loop number 1, this path, where we're going to go from the collector supply. We're going to drop base current times the base resistor to get to point B. Then we're going to drop the base emitter voltage drop to get to point E, to our emitter voltage point. And then we're going to drop the rest of our voltage to ground in emitter current times the emitter bias resistor. So there's our loop. We can relate our base current and our emitter current to our collector current with our typical relationships for BJTs, for large betas. And so now we can substitute in and have one equation and one unknown and solve for our collector current in terms of our collector supply, base emitter voltage drop, again, property of the transistor, and base and emitter resistors. So this looks pretty similar to what we had before. Same dependence of collector current on beta and the rest of the circuit. So we can go one up from there and say, all right, I have an expression for my collector current. If I want a Q point, an operating point, I'm going to want to know how this relates to my collector emitter voltage drop. Okay, so this time the collector emitter voltage drop is not equal to the collector voltage because we do have a voltage drop to get to the emitter. So it's floating partway between the supply and ground. But we can still write an expression for it. We can still start at our collector voltage. We can drop to V sub C with our collector current flowing through our collector resistor. We can write VCE, and then we can write an expression for the drop from E to ground. So getting to point C, that's what we're solving for, and this is the drop the rest of the way to ground. We know that our collector and emitter currents are comparable, so we can substitute it in I sub C here, and we get an expression for our collector emitter voltage in terms of our collector current and other things in the circuit. So this makes it very easy for us to determine cutoff and saturation. In order for I sub C to be 0, this whole term would end up being 0, so the collector emitter voltage for cutoff is the same as the supply. And likewise, if this is 0, then I just solve for IC sat by solving the equation, pulling VCC to the other side. So here's my load line. That made it pretty easy. And if I want to get my Q operating point, all I do is plug this expression in for I sub C, and I can solve for my VCE with a little bit of math and get my Q point. I might just calculate a number for I sub C from here and plug it in if I need to. Okay, now before we quit with this, let's write some expressions for our collector base emitter voltages in terms of ground and in terms of our supply and currents to get there. So we can look at our voltage at point C in terms of the supply minus the current that flows through R sub C. We can look at our base voltage in terms from the top down, our supply voltage minus the base current times the base resistor. So that's supply minus the Ohm's law drop over our base bias resistor. And we can look at the voltage at point E as just our emitter current times our emitter resistor, just total Ohm's law to get us a voltage at E versus ground. So we can write these expressions. So these are the collector base and emitter voltages versus ground, just using Kirchhoff's voltage law and Ohm's law. Then we can start relating them to one another. So we can get some useful expressions relating some of our currents that help us understand the feedback. So we go through a little bit of math. It's not necessarily intuitive, but bear with me. We can write our emitter voltage in terms of our base voltage just minus the base emitter drop. We know that's true. We can say this voltage equals this minus the drop between, which we happen to know, 0.7 if it's a silicon device. And then we can use that expression, again, plug that in here, and then relate I sub B to I sub C. And now I have two different independent expressions for the voltage at point B. So I can relate those two together, and that gives me an expression here, which the only reason we derived this was to give us an expression for base current in terms of collector current. Because remember, we did that with the collector feedback. If the collector current goes up, does the base current go up and down? So again, we have the same kind of inverse relationship. If the base current goes up, collector current goes down. So we again have a negative feedback condition. So this whole set of mathematics was basically to prove that we have some negative feedback with this arrangement, which we just proved we did, because as this goes up, that goes down. Okay. Example 5.6 from our textbook is basically just the same thing we went through with some numbers. So I will leave that to you to step through. It's very similar. Getting a Q point and a load line. Remember, go through your KVL loops where you have the voltage drop base emitter, and then solve for your collector emitter by difference, just like we've done before. And in this case, you got to go through the exercise of what would you do, what would happen to the collector current if you reduce beta, and in this case it was definitely less beta independence. So that's always a good exercise anytime you're evaluating a biasing scheme of an amplifier circuit. Is if you double beta or have it, what happens to your collector current? So you can do the math and decide for the values of supplies and resistors, have you truly achieved stability with respect to your beta, because it will change in circuit operation. You can do both the collector emitter feedback bias voltage, or biasing, excuse me. So this is an example of how that would work. I won't step through all of the KVL loops because they're very similar to what you just did, but basically use the same techniques of solving for our V sub C and E in terms of each other, writing your KVL loops like I've done, and you can get expressions for collector current again in terms of all of your resistors and your beta. This time we have an extra term in our denominator and can relate that also to your collector emitter voltage. So here's where you get your Q point, these two expressions. And then again, saturation and cutoff are even easier. If there was no voltage drop between C and E, our saturation current would just be our collector supply divided by the combo, the series combo of our collector and emitter bias resistors. And of course we would need voltage across the collector emitter equal to our collector supply to shut off the collector current. So there's our cutoff. Cutoff is VCC. Otherwise, exactly the same as the other two examples. So you can go through the derivation in example 5.7 and look at your beta dependence, calculate a Q point. So that is it for biasing schemes. Big takeaways. Why do we bias? Because someday we are going to put an AC signal in our base and we want it to completely go through and be amplified and be able to take an amplified signal out at the collector or emitter. We don't want it to all get cut off just trying to open the base emitter voltage, forward voltage bias. Forward voltage of the PN junction. Second, we can arrange our resistors and our supply voltages to effectively make us independent of beta, such that if beta changes while the circuit's operating, we don't change our collector current. And we've also seen how feedback can give us an extra measure of stability by making base and collector current inversely related the way that our circuit is arranged and operating. So for our next lecture and our next chapter, Chapter 6 and 7, we'll start evaluating what happens when we put an AC signal into our base and actually start running these circuits as amplifiers.